So welcome to the chemistry lecture series. In this lecture, I am going to cover the topic soft and hard acids bases theory, SHAB theory. This is one of the important topics from Unit 1. So this question has been asked many times in CT1 and also in the final SEM exam. So we should go through this topic as well as we should practice this question, which is important. Okay, let's see the introduction about the HSAB theory. As I said before, hard and soft acids and bases theory, that is called SAB. This theory is a qualitative concept introduced by Dr. Ralph Pearson. He introduced this concept to explain the stability of the metal complexes and the mechanism of their reactions. So using this one, you can predict both the stability and mechanism of the reactions, particularly the coordination compounds. However, it is also possible to quantify this concept based on Klopman's FMO analysis using the molecular interaction, that is based on the higher occupied molecular orbital and lowest unoccupied molecular orbital. Homo-LUMO interactions also you can explain this one. So according to this theory, the Lewis acids and bases can be further classified or divided into hard or soft or borderline types. You will see one after the other what is the hard acid or base and soft acid, soft base, and what are borderline types. We will see. So as you know that alkenes acids form hydronium ions in water and bases form hydroxide ion. This we already know. From this definition, we can say that water is a solvent. And also, Bronsted-Lowry concept you might have learned before. This can be extended upon the Arrhenius definitions as well. And they are defined as acids as proton donors and bases as proton acceptor. This we know that any acid like HCl, if it donates protons, then it is an acid. And also the proton acceptors like sodium hydroxide or the whichever accepts the proton, that is called bases. They also introduced the concept of conjugate acid base pair also. This is the basic introduction which we should know. For any solvent, we know that that can dissociate into its cation and anion. Any solvent. The cation is the acid and the anion is the base. This also we know that. And also any solute that causes an increase in the concentration of the cation will be considered as an acid. Those increase the concentration of the anion are called as bases. Okay. Now let's come to the Lewis acids and bases concept. This is one of the important concepts in chemistry, and also this understanding this Lewis acids and bases is important for understanding the SAB theory. According to the Lewis definition, further expand the definition. A base is an electron pair donor. For example, ammonia. Uh, in ammonia, the nitrogen present in ammonia has a lone pair of electrons, so it can donate the electron pair. So it is an electron pair donor. Electron pair donor is base, and an acid is an electron pair acceptor. To put it simple, acid instead of acid, I have represented it by a letter alphabet A, plus base, so I have represented with the alphabet B. So B is an electron pair donor, so I have put a lone pair electron next to B. So when this B donates this lone pair electron to A, then it forms a bond. As you know that for a sigma bond, you need two electrons. So that when the A accepts this electron pair from B, then a bond will be formed between A and B. This definition also includes the standard Bronsted-Lowry acid base reactions. Let's take an example. H plus, that is in aqueous solution. When you add HCl, you will have the proton. And when you add ammonia to the solution, aqueous ammonia, so this nitrogen atom present in the ammonia has a electron pair or a lone pair, which will donate, this nitrogen atom will donate this lone pair electron to proton, and as a result a bond will be formed, and the ammonia will be associated with the proton to form NH4 plus ammonium ion in aqueous state. It also includes the reactions of metal ions or atoms with ligands to form coordination compounds. Let's see, instead of the simple H plus ion, let's take a metal ion, that is Ag plus. We know that all the metal ions, the transition metal ions, the positive charge between the oxidation state, they exist in multiple oxidation state like plus 1, plus 2, plus 3 we have already discussed. Let's take the simple example Ag in plus 1 oxidation state in aqueous state when it reacts with 2 moles of when 1 mole of Ag plus reacts with 2 moles of ammonia, that is 2NH3. As we know that nitrogen present in ammonia is having a electron pair or a lone pair. So this will donate the electron to the Ag. As a result, 2 moles, so 2 ammonia ligands will be coordinated with the Ag, and it will form a coordination complex Ag NH3 2 with the complex with the single positive monopositive monocationic charge. You will get this monovalent charge. You will get this complex in the aqueous state AgNH3 with this is the coordination sphere or coordination. Now let's see Lewis base adduct. In addition to the concepts we discussed in the previous slide, electron deficient compounds such as trivalent boron is also categorized as a Lewis acid. So anything with electron deficient species are considered as Lewis acids. So let's take this one, trimethyl borate, this one BCH3 plus that reacts with 1 mole of ammonia. Again, this is having a nitrogen is having a nitrogen atom is having a lone pair electron pair donor. This nitrogen atom, it donates its electron pair and it will form a coordinate bond with this ammonia will form a coordinate bond with this boron species. The HOMO on the Lewis base the Lewis base is ammonia interacts with the lone pair. So look at this one. This is the ammonia, the Lewis base. It is having the electron pair. So we have represented with the low containing a lone pair of electrons. And this is the structure of the Lewis acid BF3. Similarly, you can, instead of fluorine, you can write CH3 as well to get the structure. And this lone pair will donated to the vacant orbital of p orbital of boron, and it will accept this one and it will form a coordinate bond. This applies to the BCH3 thrice as well. As a result, coordinate bond will be formed. So the nitrogen will be having a positive charge since it is donating the electron. Since boron is accepting the electron, it will have the negative charge. A Lewis base adduct will be formed. This happens mainly when the HOMO on the Lewis base, that is ammonia, interact with the electron pair in the LUMO of the Lewis acid, that is BF3 or BCH3, right? The embos of the adduct are always lower in energy. Also, a Lewis base has an electron pair in its highest occupied molecular orbital. For instance, in NH3, the ammonia case, the electron pair will be present in the highest occupied molecular orbital. So this will have a suitable symmetry, and this will interact with the lowest unoccupied molecular orbital of the Lewis acid. And the closer the two orbitals are, then they can overlap and interact in a better way, and they can interchange the energy, and the energy should be same level, and the stronger bond will be formed, that is in the adduct. So this particular species is called Lewis adduct. Okay, now we understood the concept of Lewis acid and bases. Now, to understand this SAP theory, there are certain things we should understand. The first one is the polarizability. And the polarizability is the charge separation, or for example, one species like HCl, the hydrogen will have the positive charge del plus, and Cl will be having the del minus. Why? Chlorine is more electronegative than hydrogen. So the polarization will happen, or the molecule will be polarized, all polarizable. So the polarizability is a fact, is a phenomenon by which the charges are introduced on the positive and negative end of that molecule, uh, which depends on the electronegativity of that particular atom. So the polarizability of an acid or a base plays a role in reactivity. Let's see what is a hard acid and hard base. Hard acids and bases are the size will be very small and they are compact and relatively non-polarizable donor atoms. So they will not donate the electron. Why? Because the size is small and it is compact. So the electrons in the outermost orbitals are strongly or tightly bound with the by the electrostatic interaction between the positive charge of the nucleus and the negative charge of the electrons. So the non-polarizable donor atoms examples would be nitrogen, oxygen, and fluorine. Soft acids and bases will have the opposite properties. Like hard acid and bases are small in size. Now, soft acids and bases will be larger in size with a more diffuse or distribution of electrons. When the size increases, it means the shell number of cell also increases, and there is the size distribution, the electron distribution in different shells also will be increasing, and they are relatively the interaction between the nucleus and the outermost shell valence cell will be very less. So they are relatively easily polarizable. So they can act as donor atoms. Example includes phosphorus, sulfur, and chlorine. Okay. So this SAB theory is useful to predict the thermodynamic stability or kinetic lability of the metal ligand complex. We will see the example, particularly the stability and also the kinetic lability we can determine. That's why we want to learn SAB theory or principle in the coordination compound. But there are other factors like the chelate effect or ligand field stabilization energy, which should also be considered when you are discussing the SAP theory. So the concept is very simple. Hard acids preferentially bind with hard bases. Similarly, soft acids would bind preferentially with the soft bases. Hard interaction will be stronger. Soft interaction will be stronger as well. Whereas when a hard acid interact with the instead of hard base, if it is interacting with the soft base, then obviously the stability of the complex will be lower. Are you able to follow me? Okay. So let's see the next one. Okay, now if they ask you this question, as I said, explain the Lewis acid, Lewis base concept, and what is SAB theory. The main point is I mentioned last time. Hard acid prefer to bind with hard bases, soft acid prefer to bind with soft bases, so that the bond strength will be stronger and the complex will be more stable. Just remember that point. And then uh, you have to write the differences between hard acid and soft acid. Okay, look at this table. So I have listed the properties of the hard acid. So the hard acids will have small ionic radii, so which will be opposite to the soft acids. Obviously they are easily polarizable, so large ionic radii. And hard acids will have high positive charge. This will be with less amount of positive charge or low positive charge. They are strongly solvated. These are completely filled atomic orbital. Empty orbitals in the valence shell. High energy donors will be present. Low energy donors will be present. Okay, let's see the examples for this one. So anything acid you remember. So they are Lewis acids. We already seen. So they are electron deficient. Obviously the metal cations positive charge, and also the size should be smaller. Like the alkali metals, as you know in the periodic table, lithium, sodium, potassium, the first group will be having smaller size, so that these are considered as hard acid. Whereas the transition cations, which are located or positioned in the middle of the periodic table, like Cu plus, Ag plus, Au, like mercury, uh, particularly these transition metal cation, and also not only the monovalent, the bivalent cations like Hg2 plus, palladium, cadmium, platinum are also considered as soft acids. And similarly, for the smaller ionic radiation, like other than alkali metals, alkaline earth metals also have the smaller ionic radii, like beryllium, magnesium, calcium, strontium, and tin. And also the trivalent cations like aluminum, gallium, indium, chromium, cobalt, 3 plus, and also iron and lanthanum. Similarly, silica, titanium, zirconia, and thorium. So when you, for your exam point of view, it would be very difficult to remember all these species, am I right? So for each type, like a monovalent, divalent, trivalent, and tetravalent, try to remember two or three examples and you can list it out. Similarly, mono and divalent soft acids, you can write any two or three. Okay, you don't need to write all these things, but I have provided all the examples so that you can choose on your will. And similarly, bases and soft bases. The hard bases are the have the small ionic radii, whereas the soft bases have the large ionic radii, exactly like their acids. So they are uh, uh, less polarizable. They are more easy to get polarized like that. And other than the, so you just remember you have to compare the radii, atomic radii or ionic radii first, and then electronegativity, polarizability. These are the points you should not miss. Like highly electronegative, obviously small ionic radii means it will be highly electronegative, and large ionic radii means it is more easy to polarize, and then you can remove the electron very easily from the valence cell, and therefore they are having intermediate electronegativity. Weakly polarizable, highly polarizable, low energy, low MOS. Here, same like the hard acids, we are seeing high energy, low MOS, strongly solvated. Just remember this one. And also list any two or three. I would say we are seeing that hard acids and soft acid, the species with positive charge. So why? Because they are electron deficient. Here, the bases and soft bases are electron-rich species. Obviously, they will have carry either they can be neutral like water molecule or those species with negative charge. Just remember this basic difference. Like as I said, two, three examples you can write. Water is easy to remember because oxygen. This is a neutral one. So neutral type, just write one and OH minus, and halides you can write fluoride, chloride ion you can write, phosphate, sulfate. This also easy to remember. So carbonate, sulfate, phosphate. These are very easy. Nitrate. You can choose these five, and also two halides, chloride and chloride, and water. There are other species like neutral. You can either write water or anything. So now in coordination chemistry, we have seen that the ligands, whatever the examples we discuss, are mostly amine ligand or water. They are neutral ligands, so they are considered as hard bases. So if they coordinate with the hard acid, then they will form a strong complex. Like we have seen, what would be the hard acid? Like alkali metals, alkaline metals. We have seen cation, mono, di, tri, and tetra. If they coordinate with those species, then the complex will be more stable. Similarly, the soft bases, when they coordinate with the soft acid, what is the soft acid? We have seen like Ag plus, Hg plus, Hg2 plus, platinum Pt 2 plus. No? So those cations, then if any of this soft base ligand, if it bind, for example, cyanide, if it binds with mercury or the other Ag species or platinum, this thioisocyanate also, it will form a very strong bond or a stable complex. So in this case, I would say you can write Cn, then you are adding one sulfur, that is SCN, thiocyanate. These two you can easily remember. And iodide, so this difference you should know. Here, fluoride, chloride are hard base, whereas iodide is a soft base. Why? When you move along the group, fluorine, chlorine, bromine, iodine. Iodine is present in the last one. So which means that we know that ionic radii increase along the group now. So from fluorine to iodine, obviously iodine is the last halogen, so it will have a large ionic radii. So obviously it will have a less electronegativity compared to fluoride or chloride. That's why it is placed in the soft phase. Just remember this one. And then carbonate, and these are the other species like arsenic 1, R3P, and also benzene, organic compounds, and also ethylene, R minus, H minus. sulfide, several examples. But as I said, just write any two or three. I would say iodide, CN, SEN. These three you can easily remember. So you can write this one. And now the borderline Lewis acids and bases, which means they have the intermediate properties between this hard base, or soft acid, soft base. Their properties will be intermediate. So that's why they are called as borderline Lewis acids and bases. Example would be like Lewis borderline acids means, example, Fe2 plus, the divalent cations, Fe, nickel, copper, zinc, Pb, and NO plus. Similarly, the bases, neutral 1NH3, chloride, RCl, Br minus. So here we didn't put Br. So Br minus is a borderline. So it has intermediate properties between the Lewis acid and base. And also this nitro and the sulfide, aniline, pyridine, etc. Write any two examples. Now let's move on to the HSAB principle. Usually in your exam point of view, they will ask you to write HSAB principle and write any two applications. So I will share some of the applications. You can write choose any two applications and you can explain. So this is the principle. As I told before, hard acid prefer binding to hard bases to give ionic complexes. Soft acids prefer binding to soft bases to give covalent complexes. So you can determine whether the complex is ionic or covalent in nature even based on this interaction. So when it is soft, then it will be covalent. Hard, then it will be ionic complex. Just remember that one. So the large electronegativity differences between hard acid and hard base give rise to strong ionic interaction, whereas the electronegativities of soft acids and soft bases are, as we know, mostly the same, and hence have fewer ionic interaction. And whenever the ionic interaction is few, there is always a possibility for the covalent interaction to come into play. As a result, the interaction would be covalent. And the next point you should remember is the interactions between hard acid soft base, or the other way, soft acid hard base, are mostly, which means they are not hard or soft. They are interchange, right? Hard acid soft base or soft acid hard base are mostly polar covalent and tend to be more reactive or less stable. This is what I mentioned before. Whenever it is hard acid hard base, it will be strong interaction, and also they are ionic, we have seen. But soft and soft acid soft base will be covalent, that also we know. But when they are opposite, like hard acid binds with, instead of hard base, if it is binding with a soft base, then it is polar covalent and tend to be less stable or more reactive. That is the reason why such complexes are less stable. The polar covalent compounds can also readily form either more ionic or more covalent compounds when they are allowed to react. That we will see. And now let's move on to the application of the SAP principle. So recovery of gold. So this is an area where SAP principle can be applied. As we know, it is a gold is present in a monovalent cation state Au plus. The soft metal, we have seen that, right? Soft base. So that metal ion is required in mining operation by suspending in dilute solution. Why? Cyanide is also a soft base. We have seen that. So this will react with this one, and it will dissolve the gold. 4Au will react with 8 moles of cyanide in presence of oxygen, and 1 mole of oxygen and 2 moles of water. It will form this RO-cyanide complex, that is 4AuCN2 minus plus 4OH minus. So by using this coordination chemistry or the interaction, so here gold will act as a Lewis acid and cyanide will act as a Lewis base. That is the concept we learned. So it will form a stable complex. In that way, from the water or from the mining operation, during mining operation, we can recover this one. But still cyanide is toxic. That also we know. And this is one of the questions which have been repeatedly asked in the final sem and also in CTs. Like, why is AgA water insoluble but lithium iodide is water soluble? How will you explain this one? Like, based on the SAP principle. Like AgA is a combination of soft acid. Ag is a soft acid, like gold we have seen, and iodide is a soft base. We have also seen. I told you that along the halogen series, iodide is present at the bottom. So larger size, more easy to polarize, and the electronegativity will be intermediate. Right, you just remember that one. So soft acid, soft base, while lithium ion. Um, so since Ag is a soft acid, iodide is a soft base. Soft acid, soft base interaction will be, mostly stronger, and also the chance is covalent. Am I right? Covalent bond formation is possible. As a result, they are highly insoluble. While lithium iodide is a combination of hard acid, lithium cation, smaller. It is an alkali metal cation, so obviously smaller size, and iodide is a soft base. That also we have discussed now. So hard acid soft base interaction will be weak compared to soft acid soft base. That's why Ag is insoluble in water. When you put silver iodide in water, it won't dissociate easily, but lithium iodide will dissociate easily. The reason is hard acid soft base interactions are weak. Okay, like ionic interactions. So that's what I have written here. Silver iodide, when you put in water, essentially no reaction insoluble, whereas lithium iodide will dissociate into lithium cation and iodide anion. So also not only aqueous solvent, the solubility of lithium halides in non-polar solvents also follow this order. So lithium iodide is easy to polarize. It can dissolve very easily in non-polar solvent, followed by bromine, chlorine, and iodine. You just follow this halogen series: fluoride, chloride, bromine, and iodide. So their reactivity or solubility follows the other way, from bottom to the applications of the SAP principle, other than the stability of the complexes or solubility of the complex. This is the second one. It can predict the strength of the hydrogen bond. Whether the hydrogen bond is weak or strong, you can determine. The strong hydrogen bond is possible in cases of water, ammonia, and HF. Why? Because the donor atoms like fluorine, oxygen, and nitrogen are hard bases. We already know, and their interaction with the partially positively charged hydrogen, which is a hard acid. So due to the hard acid hard base interaction, that is, hydrogen is a hard acid, and these three species, oxygen, nitrogen, and fluorine, are hard base. So hard acid hard base interaction are stronger. As a result, the hydrogen bonding will be stronger as well. And precipitation reaction also, the SAP principle can be applied. The softer acids, like we have seen that monovalent and divalent, particularly silver and mercury, Ag plus, Hg plus, and Hg2 plus. These softer acids and borderline acids, intermediate properties, like the transition metal cations like iron, nickel, copper, zinc, lead, can be precipitated as sulfides from their aqueous solution. While sulfur is a sulfide ion is a softer base, so soft acid bind with soft base. This is also very useful in ore and metallurgy, like the copper. That's why copper exists in the form of copper sulfide. So we know that copper oxide ore is possible, but why it exists in sulfide ores, or mercury is why it exists in sulfide ore? The reason is soft acid soft base interaction. So it is also determine the stability of that particular sulfide compound. And also calcium and magnesium hard acid appears as carbonate. We also know that calcium carbonate, magnesium carbonate. Am I right? So that also you can explain. And the third example, we have seen the solubility, we have seen how we can predict the strength of the hydrogen bond, and how the precipitation reactions we can apply this principle. Now we are going to again determine the stability of the compound. Lithium iodide plus cesium chloride. So when you have these two compounds in solution, then lithium obviously will bind with the fluorine atom, and it will form hard interaction, cesium iodide, soft interaction. Similarly, Agi2, lithium iodide we have seen. Now we are looking at Agi2 minus is stable, but AgF2 is unstable. What is the reason? Because Ag plus is a soft acid, iodide ion is a soft base. So soft acid soft base interaction leads to a more stable compound, that is AgI2. Whereas here it is opposite. Ag plus is soft acid, whereas fluoride is a hard base. Fluoride and chloride are hard base. We have already seen. As a result, they interact and form an unstable AgF2 minus. Similarly, COFC3 minus, this is a compound is stable, but COI6 is not stable. What is the reason? Because cobalt 3 plus and fluoride are fluoride ions are both hard acid. This is hard acid and this is hard base. So the interactions will be stronger and they are more stable. Ambidentate diagrams like SCN and NCS, thiocyanate we know SCN minus and isothiocyanate we know NCS minus. This also we can explain by SAP principle. This shows that linkage isomerism and coordination compound depends on the donor atom. Sulfur atom is a soft and nitrogen atom is a hard. So the nitrogen atom, since it is hard, it tends to coordinate with the harder acids like CO3 plus, Fe3 plus and SA4 plus. So based on this also you can determine if you have these two ligands, which one will preferentially form a stable compound or a complex with this hard acid transition metal cation. Whereas the sulfur atom, it is a softer acid, a softer base now, so it will tend to coordinate with softer acids like platinum, mercury, and copper. That's why copper exists in the form of copper sulfide or mercury sulfide. Similarly, carbon atom of cyanide is also a soft base. That's the reason. Instead of SCN, NCS, if it is binding through only you are having cyanide, it is also a soft base. So it can bind with the soft acids like platinum, mercury, and copper. Okay. So with this, I would like to complete this lecture series that is particularly the SAP theory or SAP principle from Unit 1. Thank you for watching and thank you for your kind support. Thank you.